Even without humans catching fish, fish die from a whole range of different causes. Old age, predation, disease, lack of food, these are all examples of things that cause natural mortality, or deaths that would happen without fishing. Typically, all of these things are very hard to measure out in the ocean, but luckily, there are some general relationships between how old animals get and their natural mortality rates. Scientists often represent natural mortality by just using the letter N. Scientists estimate natural mortality based on how long the fish live. Longer living fish have lower natural mortality. Some level of natural mortality is occurring all the time, but once you start harvesting a fish population, the fish you catch or kill become one of the major sources of mortality. This is termed fishing mortality and is represented with the letter F. Going back to our diagram, you can see where natural mortality and fishing mortality fit. The combination of these two gives us total mortality, represented by the letter Z. Total mortality is a measure of the proportion of fish that die each year, which is obviously important to understand for stock assessments.
By the looks of some of them that have been caught over the years, you might catch a blue eye every now and again that might be 25 kilo, 30 kilo on the odd occasion. I'm sure they're probably, I would have to say they're probably around 40 years old, probably as old as me at the end of the day.
Knowing how long a fish species lives and their mortality rate is critically important to managing a fishery. We've already discussed measuring fish age, so how do we measure mortality? Building on what we already know about the age frequency distribution in tiger flathead and extending this over a number of years, we can track the change in population for each group of recruits. Let's follow this through and look at an example starting in 2002. Here we see a graph of the age structure for the whole fishery. Along the bottom line is age in years, and along this line is the number of fish. This column represents the number of new recruits for 2002. Moving to 2003, our new recruits are now 4 years old, and as you can see, their numbers have gone down due to a combination of natural and fishing mortality. Again, in 2004, our recruits are a year older and their numbers have dropped even further. This continues each year until they all die. If we isolate the 2002 recruits and look at the change in their population over the following years, our graph looks like this. Here we have total number of fish at each age, and as you can see over the period, the number of each age class falls. This is called a catch curve and represents the total number of fish dying each year. But what we really want to know is the proportion of the stock dying each year. This is the important figure. Now, we're not going to bore you with the maths on this, but this curve can be straightened by squashing down the graph. Scientists call this a log transformation. The gradient of this line is the total mortality, or Z. The steeper the line, the higher the mortality rate. Scientists do this with a number of year groups and get an average which represents the mortality for the whole stock. This is a good example of another assumption made for the model. The mortality is the same across a number of different year classes.
One of the hardest population parameters to measure is natural mortality. Typically very difficult to get an idea of how animals die in a natural environment. Luckily, there's a relationship between growth and natural mortality, so how long something lives for gives you an indication of its natural mortality. For instance, a fish like an orange roughy that can live up to 100, 150 years old generally has low levels of natural mortality, whereas something like a squid, which might live only to 18 months, will have a high level of natural mortality. So it's that relationship between growth and age that gives us an insight into natural mortality for different fish stocks.
Let's look at examples using species that our case study fishermen catch. Blue-eye trevally are one of the longest living of our species, reaching at least 40 years old. Its catch curve looks like this. School whiting live for around 7 years, and their catch curve is much steeper. The steeper the curve, the higher the mortality rate. Let's go back to the catch curve for our tiger flathead example. If we only took into account natural mortality, our curve would look like this. If we take into account fishing mortality as well, then the curve changes to this. The whole curve gets lower and its angle changes because the stock's mortality rate increases. If we further increase fishing mortality, you can see the line getting steeper and steeper. You can also see that there are relatively fewer old fish in the population. This is one of the indicators that a stock is under considerable fishing pressure.
I reckon there's not as many big ones anymore as what there used to be. Probably the average size would be smaller since I started. But like you still see occasionally real big crow.
Going back to our stock assessment diagram, fishing mortality is directly affecting biomass change. Looking at the stocks from last year, if we know how many are dying from both natural and fishing mortality and how many are being recruited this year, then we can estimate the stocks or biomass for next year. That brings us to the end of our section on mortality. Just to recap on this section, we covered the difference between natural mortality and fishing mortality, and the process for estimating total mortality across a whole fish stock. In our next section, we'll be looking at how the gear we are fishing with and how discards affect the information scientists collect to estimate recruitment, age and growth, and mortality.